Hello everyone, my name is Arshid Abbas and I'm here to discuss my topic, Introduction to Continuous Random Variables. Continuous random variables are variables that can take any value within a given range. They are essential in statistics and probability theory, allowing for the modeling of phenomena where outcomes are discrete. Understanding their properties and distribution is crucial for effective data analysis. Here's an example. The height of individual in a population can be modeled as a continuous random variables because it can take any value within a realistic range, such as 150 cm to 200 cm. Key characteristic. Continuous random variables are defined by their probability density function, which describe the likelihood of variable falling within a particular range. Unlike discrete variables, they do not have specific values, but rather a continuum of possibilities, making them essential for various statistic application. Example, temperature recorded through the day is a continuous random variable. The likelihood of a temperature falling within a specific range, let's say 25 degrees Celsius to 30 degrees Celsius, is described by a probability density function. Common probability distribution. Superior probability distribution are associated with continuous random variables, including the normal, exponential, and uniform distributions. Each distribution has unique properties and applications, making them suitable for modeling different types of data and real-world scenarios. Example, measuring the weight of fruit in kilograms since weight can take any value. Let's say 2.35 kg and 2.48 kg. It is continuous and described by a probability density function. Common probability distribution. Normal distribution. Test score of student in class. Exponential distribution. The time until a machine part fails. Uniform distribution. Rolling a perfectly balanced spinner where outcomes are equally likely. Conclusion and implications. Understanding continuous random variables and their probability distribution is vital for effective data analysis and decision making. Mastery of this concept allows researchers and analysis to model complex phenomena accurate, leading to better insight and outcomes in various fields. Let's say in weather forecasting, continuous random variables like temperature and rainfall are modeled using probability distribution, enabling accurate prediction and better decision making for agricultural and disaster management. Thank you.
Hey ma'am, my name is Salahuddin K. Adam. I am reporting number 2. Now, let's talk about expected values for continuous variable. Expected variable for continuous variables refers to the predictive value or means outcome typically calculated using probability distribution or regression models, reflecting the central tendency of the data. Okay, next, I wonder how long we would have that to wait per person to see people. In other words, StatQuads wants to know the expected value for waiting time, which is something we can measure. And after 10 seconds, you meet someone. So you and StatQuads decide to keep track of that by putting a dot on this number line at 10. The next person we meet show up after 30 seconds. Then StatQuads says, ug collecting all this data is taking forever. In the data means we will have more to collect. Next is calculating the slope of the line. Slope is the ratio of the change in y and the change in x. Slope m equal to change in y, change in x over change in x. This can be calculated using 2 points on the line with the formula. Slope m equal y2 negative y1 over x2 negative x1. But what if we want different interval size like 5 or 2.5 seconds? Then StatQuads notice that the data are plotted using 10 seconds intervals and says, so you tell StatQuads. StatQuads is a term used humorously to describe a fictional or exaggerated version of statistical analysis. It often refers to overcomplicated or misleading interpretation of data blending statistically concept with absurdity typically used in internet memes or discussion. So, thank you for entertaining, ma'am. So, yun lang po.
Understanding normal distribution, the foundation of statistical analysis. Introduction to normal distribution. In this presentation, we will explore normal distribution, a fundamental concept in statistics. Understanding this distribution is crucial for conducting statistical analysis and interpreting data. We will cover its properties, significance, and applications in various fields. What is normal distribution? Normal distribution is a probability distribution that is symmetric about the mean. It represents data that cluster around the mean, with most occurrences falling within a range defined by the standard deviation. This results in the characteristic bell-shaped curve. Key characteristic of normal distribution include symmetry, the mean, the median, and the mode being equal, and the 68, 95, and 99.7 rule. This rule indicates that approximately 68% of data falls within one standard deviation of the mean. Normal distribution is vital in statistics as many statistical tests assume data is normally distributed. It facilitates hypothesis testing, confidence intervals, and regression analysis, making it a cornerstone of inferential statistics. Standard normal distribution. The standard normal distribution is a special case where the mean is 0 and the standard deviation is 1. This standardization allows for easier comparison of different data sets by converting values into z-scores. Application in real life. Normal distribution is used in various fields such as psychology, finance, and quality control. For example, it helps in assessing test scores, predicting stock marketing trends, and ensuring product quality through statistical process control. Central limit theorem. The central limit theorem states that the sampling distribution of the sample mean approaches a normal distribution as the sample size increases. Regardless of the original distribution, this theorem underpins many statistical methods. Common misconceptions. A common misconception is that all data is normally distributed. In reality, many data sets may exhibit skewness or kurtosis, which can affect analysis. It's essential to assess the distribution before applying statistical methods. Limitation of normal distribution. While normal distribution is widely used, it has limitation. It does not adequately describe data with extreme values or outliers. In such cases, alternative distribution may be more appropriate for analysis. Conclusion. In conclusion, understanding normal distribution is essential for effective statistical analysis. Its properties and applications make it a foundational concept in statistics, aiding in data interpretation and decision making across various fields.
So, good day everyone. I am Haidar El Alamada and I am the reporter for the topic 4.4, the normal approximation to the binomial and Poisson distribution. Normal approximation to binomial. Recall from chapter 5 the binomial probability distributions. Number 1, the procedure must have a fixed number of trials. Number 2, the trial must be independent. Number 3, each trial must have all outcomes classified into 2 categories. And number 4, the probabilities must remain constant for each trial. So they have this symbol here. The mu is equal to NP, and the next one is sigma is equal to NPQ. So the next one is the same as the first, the sigma, square root of NPQ. If NP is greater than equal to 5 and NQ is equal to greater than equal 5, then the binomial random variable has a probability distribution that can be approximated by a normal distribution with the mean and standard deviation given as. So just like what I said before, this is mu, NP, and sigma square root of NPQ. Is what this tells us that if both NP is greater than equal to 5 and NQ is equal to greater than equal to 5, you can use the normal distribution. So compute the mu and the sigma using the formulas above, then use the method we for normal distributions. So they are here a formula that we can use for the problem about the normal distributions. If not saying if an NP is less than 5 or NQ is less than 5, you will use software calculator table 1A or calculation with the binomial probability formula. So the formula here is P open and close parentheses with X is equal to NC X times P raised to the X times Q raised to the N minus X. Using a normal distribution to approximate a binomial distribution, number 1, verifying that up to greater than equal to 5 and NQ is greater than equal to 5. If these two conditions are not satisfied, then you must use software calculator or table 1A or calculation with the binomial probability formula. Number 2, calculate the parameters to mu and sigma. And number 3, draw the normal curve and label the graph. The value of X will be entered in a special way. It is described below. Since the binomial distribution is discrete probability distribution, we want to approximate it by using normal distribution. So with continuous probability distribution, we will need a continuity. The continuity identify the discrete value X which happen to be the number of successes. Replace the value X with the interval X minus 0.5 to X plus 0.5. The main reason for this is create an area that will represent the probability of the number of X. Recall that Px is equal to A is equal to 0. Example hashtag number 1. A country hospital is expecting to record 100 births next month. What is the probability that more than 55 girls will be born out of those 100 births? So number 1, clearly this is a binomial distribution. So your N is equal to 100 and then your P is equal to 0.5 probability of girls being born. And then your Q is equal to 0.5. Number 2, NP is equal to 100 times 0.5 is equal to 50. NQ is 100 times 0.5 is equal to 50. Thus, we can use that normal approximation, and MU is equal to 50 and sigma is equal to 5. The number 3 is X is equal to 55 number of successes. Since we are going to use the normal approximation to binomial, we will need change X 55 to the interval of the 55 minus 0.5 is equal to 54.5 to 55 plus 0.5, 55.5. So we are here the example of the liberal, the normal curve graph estimation. We have the 55 girls being born, and here your mu is 50 and your value of x is 55, and this is in your side is 55.5 and the 54.5. And back to our question, what is the probability that more than 55 girls will be born out of those 100 births? By the normal approximation to binomial, we have the Px is greater than equal to 55.5. So this is a example for the curve or graph. So we will see on the solving. So we are solving the problem of Px is greater than 55.5. Just as before, we need to convert x to z. So z is equal to x minus mu over sigma is equal to 55.5 is minus 50 over 5. So they can substitute it. The value of x is 55 based on the curve or the graph. So 55 your value of your x, and your value of your mu is 50, and then the value of your sigma is equals to 5. So if you can multiply it, or if you can solve it, is you have this 1.1. So this is your value of your z. So now that we have the z, we can use table A2 to find the corresponding probability. The table gives us PZ is equals to greater than 1.10 is equal to 0.8643. Since we are trying to find the Px is greater than 55.5, then the Px is greater than 55.5 is equal to 1 minus 0.8640 is equal to 0.1357. If you want to use the binomial probability on the mini tab, use the cumulative probability option with input constant 55. You will get a result of 0.864373. Subtract that result from 1 to get 0.13562. On the 83, you will use one binom CDF. They have the 100, 0.5, and 55. The second topic, the Poisson probability distribution. The Poisson probability distribution provide a good model for the probability distribution of the number of rare events that occur randomly in time, distance, or spaces. The random variable of x is said to follow the Poisson probability distribution if it has a probability function. So example here, the P is close in open parenthesis with x is equal to e, the negative to lambda, and we have the lambda raised to x over x, and for x is from 0, 1, and 2. Where px, so this is our definition, px is equal to the probability of x successes over the given period of time or space given of lambda. So the sign here or the symbol here is that we call the lambda. The expected number of successes per time or space unit lambda is greater than 0. And E is equal to 2.71828, the base for the natural logarithms. And the mean and variance of the Poisson probability distribution are the mu is equal to big X and open and close parentheses with X is equal to lambda. And then second here is the sigma raised to the 2 and E open and close bracket open parentheses and close parentheses X is minus 2 mu squared is equal to lambda. And I have an example of this. A life insurance company insures that life of 5,000 men of age 42. If actuarial studies show the probability of any 42-year-old man dying in a given year to be 0.001, the probability that the company will have to pay for claims in a given year can approximated by the Poisson distributions. So we can do here is to identify the given problem, the given, to substitute a formula. So the 5,000 here is equal to, so they have the px or close open parenthesis is big X is equal to 4. So the 4 here is from the pay per claims over n, then equals to 5,000, which is your men of age 42, and your P is the given year to be 0.001. So if you can solve it or using your calculators is you can have the answer 0.1745. So that's all. Thank you for listening and have a nice day. Goodbye.
Good day, everyone. My name is Shane Therese Almonasid, and today I'll be presenting an overview of the exponential distribution. We'll explore its properties, real-world applications, and its connection to the Poisson distribution. So, what is exponential distribution? The exponential distribution describes the probability of a continuous random variable, such as the time until an event occurs. For example, think about waiting for a bus, the lifespan of a device, or the time between phone calls. These are common scenarios where the exponential distribution applies. It's defined by a single parameter, lambda, which represents the rate of occurrence of events. This distribution is continuous, positively skewed, and always positive. Properties of exponential distribution. Let's look at the main properties. We have three main properties, which is single parameter, positive skewness, and memoryless property. Let's start with single parameter. Lambda, or the rate of occurrence, determines the shape and scale of the distribution. Positive skewness. The tail of that distribution extends to the right beyond the mean. Memoryless property. This unique feature means the probability of an event occurring in the future does not depend on how much time has already elapsed. We'll explore this with an example later. Probability density function, or PDF. The PDF of the exponential distribution is expressed as f of x equals to lambda e raised to lambda x, where lambda is the rate parameter. X is a random variable, typically time, and E is the base of the natural logarithm. This function helps us understand the likelihood of different time intervals. Cumulative distribution function, or CDF. The cumulative distribution function is f of x equals to 1 minus e minus lambda x, or f of x is equals to 1 minus e raised to lambda x. This equation represents the probability that an event occurs within a given time frame. The CDF is particularly used for answering questions like, what is the likelihood the next phone call happens within 5 minutes? Memoryless property example. One fascinating property of the exponential distribution is its memorylessness. Imagine a light bulb with an exponential lifespan. The probability of its burning out in the next hour is the same whether it's brand new or has been lit for 10 hours. This property has important implications in fields like reliability testing and queuing theory. Next is relationship with the Poisson distribution. The exponential and Poisson distributions are closely connected. While the Poisson distribution describes the number of events in a fixed time interval, the exponential distribution describes the time between these events. This relationship arises naturally because the exponential distribution is the waiting time distribution for the Poisson process. In conclusion, the exponential distribution is a versatile tool for modeling and analyzing time-to-event data. Its unique properties, like memorylessness, make it ideal for solving problems across diverse fields, from customer service to software reliability. This ends my discussion, and I hope you learned something about my topic. Thank you.